Yes. We're good to go. Action.
So we've got a battery. It could be a power pack. We're going to use a battery because the effect's easier to see. And when we're just measuring the voltage of the battery, we get 12.74 volts. But then we connect the circuit and the lights go on. The voltage drops. The current's kind of stable-ish around 4.8. The voltage is dropping and dropping and dropping. It's going to stabilise. But why is it that when current flows, the voltage drops? So we always thought that the voltage of a battery was like the chemistry, it's the fixed voltage, right? So why is it dropping? What does that tell us? So the problem is that our model of the battery is flawed, right? Because our battery, all we've been drawing up until now is like a series of cells drawn together, but in fact those cells they're not perfect. Inside those cells there's metal, and we know inherent to the metal, and in fact like the chemistry inside the battery as well, is there's a bit of resistance. And so you might notice that when you use your cell phone a lot, it gets hot. So lots of current is going round and round in circles inside your cell phone, and it heats up. That's electrical energy turning into heat energy inside the battery. And so the problem, what we're striking here, is that there's resistance inside the battery, and so the voltage that we're measuring is reduced because we're dropping some voltage across that internal resistance, that resistance inside the battery. And so instantly, when we disconnect the circuit, the battery voltage jumps up as the chemistry starts to recover from having the current drawn out of it, and instantly, when we connect it, that voltage drops back down. And that's because as we're pulling current out of the circuit, there's a V equals IR, current times resistance, inside the battery that's getting subtracted away from the voltage of the battery, which just depends on the battery's chemistry. So our problem is the model of the battery doesn't include the fact that there's resistance inside it, but there is resistance inside it, so we have to include that.
And does the resistance inside it increase as we add more?
Yeah, exactly. So as a battery goes flat, there's still plenty of chemicals in there. So even quite a flat battery, you'll often measure the voltage that you should measure on it, but as soon as you connect it to a circuit, nothing happens. Or if you keep measuring the voltage, that voltage will go really, really low as soon as you try and draw any current out of it. And that really, really low voltage, as soon as you try to draw current, shows us that the internal resistance is getting bigger and bigger and bigger inside the battery. And so as soon as we try to draw even the smallest bit of current, most of that voltage is dropped across the internal resistance, and there's only a tiny little bit that's left to drop across our circuit outside of the battery. As the battery goes flat, the internal resistance increases, and that means we drop more and more voltage across the internal resistance inside the battery. And so our lights go dimmer, or if we're trying to start our car, it starts off going chicka, 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 and then it goes chicka, 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 as the voltage of the battery rapidly drops as that internal resistance rapidly increases. The terminal voltage of the battery. So the terminal voltage is what we've got here, the voltage that we're actually measuring, whereas the open circuit voltage, the voltage when no current is flowing, is the voltage that's due to the chemistry of the battery, where we're not pulling any current out of it at all. So should we draw some pictures?
Yep.
We got both of them on here.
Yep.
So this is like this left-hand one's like our old model of the circuit with just a power pack and a voltmeter and a whole lot of bulbs. And what should happen is that as we close the switches and begin to draw current out of the power supply, we should see the voltage of the power supply showing across the bulbs. But as we just saw, that's not what happens. So we've got to change our model of a power supply. And the way we do that is this dotted blue line here represents like the battery. And so inside the battery, as well as having the chemistry, same for a power supply, right? As well as having the chemistry that generates the electrical potential energy, we've also got an internal resistance, and the symbol we use for that internal resistor is just a little lowercase r instead of capital R. And so what happens is that as we close the switches and begin to draw more and more current, the more switches we close out of that battery, the more current that flows through this top loop of the circuit, the greater the V equals IR is across that resistor. And the voltage that we drop across that resistor is subtracted off from this voltage here. And so we can calculate the voltage that we measure in our voltmeter here using an equation that looks like the voltage we measure is going to be equal to the voltage due to the chemistry of the battery, which we use the symbol epsilon for, the open circuit voltage, minus IR. That R is the internal resistance of the battery. So the terminal voltage is just equal to the open circuit voltage minus the voltage drop across the internal resistance. The only exception to that is if we turn around the direction of current flow, if we reverse the direction of current flow, like if we're charging the battery, if we're putting charge back into the battery, then the terminal voltage we measure is going to be equal to the chemistry of the battery, the voltage because of the chemistry of the battery, plus IR instead. And so when we're charging a battery, we always have to have the terminal voltage of the battery higher than the voltage that we're trying to get it to, so that current flows through that internal resistance. If we just had the charging voltage equal to the voltage due to the chemistry of the battery, no current would flow. You'd have two equal and opposite voltages trying to push charge in opposite directions, and neither would win. So to charge a battery, we're going to have the voltage we're charging it at higher than the open circuit voltage. So for charging, that becomes a plus.